Welcome to iLecture Online. The second part that's really important about Schrödinger equation, the wave equation on which it is based, is that fact that we need to be able to normalize the equation. What do we mean by that? Well, first of all, we realize that the wave function by itself has no physical meaning. But when we square the wave function, it represents the probability of finding the particle in a particular location. If we then go ahead and sum up all those probabilities of all the various locations where the particle can be, that gives us the total probability of all locations of that particular particle. Now, since it represents probability, you can never have greater than 100% probability of finding the particle, which means when we add up the possibilities, the probabilities of all the places where the particle can be, the total should never be greater than 1. And the number that you typically end up with will be greater than 1, so what we do is we divide that result by itself to make it equal to 1, which is called normalization. Once we do that, then any snippet of probability, let's say we want to find the particle in this particular region, it will then be a small fraction of 1, the probability of finding the particle there, rather than everywhere else. Notice, to do that, we simply take that integral of the probability density function over all of space and set it equal to 1. If you do this for a single dimension, for example the x dimension, it simply becomes equal to this. Instead of integrating over the whole volume of space, we're simply integrating over a single dimension. And sometimes we don't need to integrate from negative infinity to infinity because there are physical limits to where the particle can be, and we just simply have to integrate over the possible dimension that the particle can be in. There are some additional conditions that the wave function needs to adhere to. For example, the wave function must be continuous and single-valued. Just like a function in algebra, when you plug in a certain value for x, you cannot have two values for y. It's no different here. For every position in x, there can only be one specific value for the wave function. Also, the derivative of the wave function must be continuous and single-valued as well. We need to be able to normalize the function, just like what we explained here. That's a very important aspect of the probability density function. And finally, when we integrate the probability density function over all of space, it has to be a finite fixed number, a finite constant. If it's infinite, then it cannot be normalized. So whatever the function is, when we integrate it over all of space, it has to be a finite number. We divide the number by itself, which is called normalization, and then we have what we call a valid probability density function that can represent the probability of finding a particle anywhere in space. And that's what we mean by normalization of the wave function.